last term, and you just replace product with dot product, because that's the only vector product you learned so far. So it must be dot product. Right? Okay. So the sum of kinetic energy will be the sum of velocities term, because the kinetic energy of just one particle, which is 1/2 m1 v1 squared, will end up being 1/2 m1 and center of mass velocity squared plus, so 1/2 and 2 cancels, you just get VCN dotted with v1 relative to center of mass, and then 1/2 and 1 v relative velocity squared. So the kinetic energy of a particle will have three terms. One is the center of mass, another one is a dot product, and another one is for the relative velocity. So if you sum them together, all of the particles will give you a term with the center of mass velocity squared. The first particle will give you m1 times VCN squared. The second particle will give you m2 times VCN squared. So if you add them together, you get m1 plus m2 times blah blah plus blah 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 until mn times VCN squared. They are all timing. They are all multiplied by VCN squared. So you know you just need to sum all your masses. That's the first term. Oh, okay. For the second term, the mass will be different and the relative velocity will be different. For the first particle, you need to use m1 and the relative velocity of the first particle. For the second particle, you need to do m2 and the relative velocity of the second particle. So you get the VCN is the same for all of them. And you are dotted with the sum of m1 and all the relative velocities. It was terrible, but this term will disappear later. But because they all have VCN, that's why you can take it out of the parentheses. And when you add all the particles, you are just adding the mass times the relative velocity. That's the second term. Okay? And for the last term, there really is nothing you can do about it. There's mass of first particle and relative velocity of the first particle. So you can only add, the only thing you can do is to add them all together. M1 and the relative velocity of the first particle, M2 and the relative velocity of the second particle, and all the way to the last particle. So that's what happens to these three terms when you add all the particles together. Now, this thing looks terrible, but if you look at the first term, it's going to be the total mass times VCN squared, so it's not that bad. And for the last term, we're just going to call it the internal kinetic energy, so you can say like 24 inch of space. For the second term, I'm going to show you right now that it's actually 0. Okay? If you look at here, the mass times the relative velocities, remember that the relative velocity can be written as the difference between the velocity of the first particle and the velocity of the center of mass. So if you add the mass times the relative velocity together for all the particles. You are adding their mass times the difference of the velocities. Okay? Now, within all the parentheses, there's VCN. So you are going to subtract M1 VCN plus M2 VCN plus all the way to Mn VCN. So that will be the sum of the masses times the center of mass velocity. That's the second term in the parentheses. For the first term, you just add them together. It's M1 V1 plus M2 V2 plus Mn Vn. Okay? Now, what is the sum of the velocity of the particle times the mass of those particles?
Acceleration.
It must have something to do with velocity because you're not dividing. So the difference of velocity divided by time is acceleration.
Yeah.
Something to do with center of mass. Center of mass velocity will be the mass of all the particles multiplied by their mass. So will be the velocity of the particles multiplied by the mass and then divided by the total mass. Right? So the first term is just the denominator of this times the total mass. And the second term is the same thing. So it's 0. Okay? This ugly cross term turned out to be 0 because this parenthesis is 0. Okay? So at the end, we are left with the first and the third term. The first term is going to be called KCM, which is 1/2 the total mass times center of mass velocity squared. So it is just like the kinetic energy of center of mass itself, 1/2 mv squared. But you are using the total mass of the system and the velocity of the center of mass. The third term, which is a bunch of energy added together, will be called internal energy. It is just the energy of the particles caused by their relative motion to the center of mass. And we just call all of this sum to be the internal kinetic energy, saving us like 30 inches of spaces. So the total energy of a system, the total kinetic energy of a system becomes the kinetic energy of the center of mass plus the kinetic energy caused by the internal motion of the particles relative to the center of mass. This is more useful because now you can see where you can easily tell the kinetic energy of the center of mass. If I am a system, this is my center of mass around here, and I'm moving like this. My center of mass is moving. It has a center of mass velocity So I have center of mass and kinetic energy. But because my body, the part of my body is not moving relative to the center of mass, so the internal kinetic energy is 0. Okay? Now, if I am spinning like this, the center of mass is always staying at here. But my body has kinetic energy. What is the kinetic energy of me right now? Is it internal or center of mass?
Internal?
Good, internal. Because my center of mass is not moving, but my shoulder is moving relative to my center of mass. It's going here, it's going there, same with my leg. So even though my center of mass is not moving, me as a system still have kinetic energy due to this relative motion of the part of my body. Okay? So again, if the center of mass is basically staying in the same place and the part of my body is moving relative to my center of mass, I have internal kinetic energy. So what I'm going to show you later is called windmill. Remember, if the center of mass is basically in the same place, I do not have center of mass kinetic energy. Alright? So this is windmill. Oh, alright. Thank you, thank you. So, when I'm doing windmill, do I have center of mass kinetic energy?
Yes.
A little bit, okay. But my body looks more dangerous, more scary than just the energy of my center of mass. Because all my leg is swinging relative to my center of mass. They have relative velocity to my center of mass, and I have internal kinetic energy. Okay? Alright, one last example. This is called backhand flip. So, when I'm doing backhand flip, do I have center of mass kinetic energy? My whole body is moving. But I'm not just moving my body, I'm flipping, so I also have internal kinetic energy.